So in our notes today, we're going to look at Descartes' rule of signs. You can pronounce it as Descartes. He's French. I don't really know how to pronounce his name, but I'm going to call it Descartes' rule of signs. So I had kids last class period ask me some questions about graphing polynomials like we did here. Graphing polynomials using the rational zero theorem. So a lot of students ask me, especially after this first question, Ms. Tapia, we went through like 3 different zeros before we actually got to a zero that actually worked. So they were saying, is there any shortcut that we can use? Yes and no. Descartes' rule that we're going to go through today will help you minimize the number of times you have to use synthetic division, but it's not always going to work. So I'm going to kind of be very upfront from the beginning. It won't always work, but when it does, it will help you solve your question a lot quicker. And I'll show you guys how to solve those questions in a bit. So the first thing, in Descartes' rule of signs, in many cases, the following rule will be helpful in eliminating possible zeros from a lengthy list. So as you saw last class period, we had, I think at one time, up to 18 different zeros that we would have potentially had to test. So that will help you hopefully eliminate about half of those right away. Once we do that, in order to understand the rule, first we're going to have to look at the variations of signs in your polynomial. When I say variations of signs, it's going to be pretty much looking at the coefficients that you have for each of your terms. So when a polynomial function has, I rewrote it twice. When a polynomial function is written in standard form, a variation sign occurs when your consecutive, if I can spell it correctly, coefficient with opposite signs. So I'll read that again. When a polynomial function is written in standard form, a variation in sign occurs when consecutive coefficients with opposite signs pretty much show. When you see that it's going from one sign to the other, that's pretty much when you're going to have a sign variation. This sentence here that I'm crossing out, I completely forgot to continue the sentence, so ignore that part. So for instance, in this question here, it says, how many variations in signs do you have for this function? So I keep it very simple, and I'm going to look at every single term. I'm going to look from here to here, from here to here, all the way down to my constant. So I just need to know, as I go from positive 4 to negative 3, does the sign change? Yes or no? Yes, it does. From negative 3 to 7, does the sign change? Yes. From 7 to x squared? No. From x squared to negative 6x? And from negative 6x to negative 1? No. So in this problem, how many times did the sign change? 3 times. That's what I'm talking about when I say a sign variation. So in this case, there are 3 sign variations. These sign variations are going to help you determine whether you have positive real zeros or negative real zeros. So this whole kind of thing that we just did will help us determine how many potential positive answers we'll have and how many potential negative answers we have. Again, this won't always work, but for some of the questions that we have, it will work. So in Descartes' rule of signs, it says, given a function f of x written in standard form with real coefficients, if you have positive real zeros that are going to be part of your answer, it's going to equal to the number of sign variations for f of x. So just like how we did above, f of x, if this was asking for the positive real zeros, I would say there's a potential to have 3 positive real zeros. It also says, or your positive real zeros can be less than that number as long as you're subtracting it by any even number. So when I say any even number, I'm going to show you guys what that means specifically on the next question. The other type that we're going to have is negative real zeros. So with positive real zeros, we're looking at f of x. For negative real zeros, we're going to look at the number variations of your signs for f of negative x. So as you notice, f of negative x and f of x are not the same. So that means, what do you think we're probably going to have to do with that negative x? If we have f of x, how would we find f of negative x? Plug it in. So we would have to replace that x with a negative x and then simplify. So we're going to do that for the questions below. And the last thing that it says for the negative real zeros is that after you find the number of sign variations for f of negative x, you can use that number of sign variations or less by any even number. And I'll show you what that means again in part 1 at the bottom. The last thing that it says is with Descartes' rule of signs, repeated zeros are also included. So anytime you have like 0 that you're going to hit the x-axis at the origin, it'll also compute that as well for you. So let's go ahead and look at part 1. So part 1 says to state the possible number of positive and negative real zeros. Again, these are possible. Just like how the rational zero theorem is possible rational zeros, this is going to be possible positive and negative zeros. So we're going to start by looking at question number 1. So with question number 1, the first thing I'm going to do is identify the positive real zeros, the possible positive real zeros. It's like a tongue twister. So I need to see for f of x from here to here, here to here, and here to here, is there a sign change? So from x cubed to x squared, yes, there is a sign change. So I'm going to put a y below that. From negative x squared to 2x, again, that is another sign change. And from 2x to 1, that's also, well, actually, this one is not a sign change, so no. How many times did the signs change here? Twice. So for my possible positive answers, and when I say possible positive answers, I'm talking about your possible positive zeros. So far, there's 2. I'm going to go back to the top of the page and mention one last thing. I said it could be equal to the number of variations, which we know for this question is 2, or it can be less than that number by an even number, so by pretty much a factor of 2. So when I say by a factor of 2, whatever number you get for your possible positive 0, take that number and subtract 2. What's 2 minus 2? 0. So we can either have 2 positive answers, 2 possible positive zeros, or we can have 0 positive zeros. We just have to actually solve it to see. If I was to do 0 minus 2 again, what's 0 minus 2? Negative 2. Does it make sense to say I'll have negative 2 positive zeros? There's no such thing as having a negative positive 0, so we don't go past 0. Okay, so we're going to either have 2 positive answers or 0 positive answers for this question. Okay, that's one part. Part 2 is finding the negative zeros. You guys told me before, what do I need to plug in to find that negative one? A negative what? Negative x. So take that function of x. I'm going to write this in red. So we're going to have f of negative x. We're going to substitute in everywhere I see an x. We're going to plug in that negative x. So far we're just using Descartes' rule of signs. On the next page, I'll actually apply it to graph a problem to show you how it looks when you're solving. So far, we're just trying to see what are the possible positive answers and the possible negative answers. All right, just like we did before, well, back when we did even and odd functions, we're going to simplify. So negative x to the third power is going to give you a negative 2x to the third power. Even though it's being negative, this negative x is being squared. So I'm just going to rewrite the negative in front and make it a positive x squared. 2 times negative x is going to give me a negative 2x, and then I'll add 1 at the end. So just like I did before, I need to check my signs. So from here to here, here to here, and here to here. Raven, is there any sign change in the first one? Second one? Last one. Okay, good. So it looks like there's only one sign change. So that means for any possible negative answers, or negative zeros, it looks like there's only going to be one. Remember, at the very top of the page, I said it could be the number of variations for the signs of f of negative x or less by an even number. Okay, well, the even number that we always check with is 2. If I was to take 1 and subtract 2, what would you get? It doesn't make sense to have negative 1 negative possible answers. You can have negative 1 as a solution, but you can't have negative 1 possible solutions for that. That doesn't make sense. So there's only one possible answer here. You're probably going to have only one negative answer. Yes, ma'am. What do you mean? Nope, that's what I was looking at. So if you use PEMDAS, and I'm going to write this along the side for PEMDAS, we're just simplifying. So does that make sense? In the parentheses, you're going to do that squared. And when you square something that's negative, it turns positive, which is why I'm not going to make this a plus negative. You're just going to keep it negative positive x squared. Yes, ma'am.
So you probably will only have one possible negative, or you will.
So it's a possibility. So just like how the rational zero theorem gave you possible rational solutions, this is doing the same thing. It says when you're solving, you're probably going to have 2 positive answers, or you might have no positive answers. For the negatives, it's saying, okay, well, you're probably going to have 1, but there's still a possibility you might not. More than likely, though, it looks like for this one, you might have 1. So let me go ahead and I'm going to make one last thing that'll help you with identifying, okay, how is this useful to me? I'm going to make a little chart. So look at the chart first before you graph it or draw it. It's like a tic-tac-toe board. And I'm going to put the signs that I have. We have positive, negative, and there's one sign that we haven't used, but you want to put it, and that's the little I. What does I stand for? Imaginary. So as you know, hopefully from Algebra 1, you can have imaginary solutions. We usually don't write them, and Algebra 2 technically. We usually don't write them, but it's possible that you will have an imaginary solution instead of a real one. This Descartes rule only finds the possible positive and negative real solutions. So far for positive, we can have 2 answers or 0 answers for this. So 2 or 0. For the possible negative answers, it looks like we can only have 1. And as we saw before, when we subtract 1 from 2, we'll get a negative answer. So you don't want to use a negative, just rewrite 1 again. Okay, so how is this chart useful? Look at the degree for this. Francesco, what's the degree for this polynomial? What's the degree for this polynomial? 3. What does that 3 mean? It is a degree. Kylie, help him out. What does that degree mean? There has to be 3 zeros. There's a maximum of 3 x-intercepts that we can have. If we look vertically, we have 2 possible positive answers and 1 possible negative answer. What's 2 plus 1? 3. So far, if this is your possible solutions, that'll mean that the imaginary solutions will be none because you want to have a total of 3 answers for your solution. Okay, well, this last one's going to be different. If we have no positive answers but 1 negative, how many imaginary would we need in order for it to be 3 solutions? 2. So what this chart tells you is where to start when using rational zero theorem. If you were looking at this chart, would you start with the positive solutions or the negative solutions? Because let me be clear first. Imaginary, this is as a last resort. As a last resort, that says, okay, if I have 2 possible imaginary solutions, let me simplify the negative first, and then I'll find the imaginary. So between positive and negative, what would you probably start with if you were going to simplify using rational zero theorem? Positive, because you're going to have a higher chance of getting one of those 2. So in green at the top, I'm going to write this little note to yourself. Check for positive, that says positive, first. So if you were solving the rational zero theorem, this is a little reminder to yourself, check for your positive answers first, because you have a higher possibility of getting one of those answers to actually show up for your solution. So this was negative, this was positive? Yeah, same thing. I would still check for negative first because you have a higher possibility of getting a negative. All right, I'm going to do one more with you guys, and then I'll have you guys try one, and then we're going to do one of the graphs on the next page. So let's look at example 3. In example 3, we're going to do the same process we just did. We'll do the chart at the very end. Okay, so first things first, let me go ahead and check how many positive zeros I'm going to have. So I'm going to go from here to here. There is no sign change. From here to here, there is no sign change. So for my positive solutions, how many possible positive zeros will I have? 0. So there's probably not going to be any positive solutions here, and that's okay. Is it in standard form? It's missing the x squared and the x. It's not going to affect your signs at all because think about it. If you plugged in that x squared and the x, it would be 0 in front. There's not really a sign for that. So we're going to look at the negatives. So I'm going to take that negative x and I'm going to substitute it in for the equation. And just like me and Kennedy talked about earlier, be careful with those signs. Negative x cubed plus 27. If you need to write PEMDAS along the side to remind you how to simplify, make sure you write it. And remember, you're going to do the exponent first with what's being multiplied, and you're going to simplify that first. You're going to have 2. This being squared is going to turn, or excuse me, raised to the 4th power is going to turn positive. This raised to the 3rd power is going to turn 21 negative. And then the 27 at the end is just 27 at the end. I'm going to go from here to here and here to here. Megan, as I go from 2x to the 4th to 21, is there going to be a sign change, yes or no? Yes. And then what about from negative 21 to 27? Yes. So how many sign changes did we have? 2. So for my negatives, there's going to be 2. Okay, we already talked about this before. 0 minus 2 is going to give you a negative 2. Can you have a negative number of positive solutions? No, it doesn't make sense. If I was to subtract 2 from 2, what's 2 minus 2? 0. Okay, that's actually, we can put 0. 0 is okay to put, but we can't put a negative number. So to organize what possibilities we could have to help us figure out what we're going to solve first, I'm going to zoom out just a bit, and I'm going to make that same chart that I made before. So we'll have positive, negative, and imaginary. Always fill in the positive and negative first, and imaginary is my favorite because it's literally whatever missing root we need. So if I look at the degree for this entire polynomial, Juan, what's the degree for this polynomial? 4. So that means for my total positive or my total zeros, not positive, my total zeros, I should have 4 total. Okay, so for positive, we already have nothing. We already said if you subtract 2 from nothing, you're going to get a negative. So we're just going to put 2 zeros at the top. And then for the negative, we can either have 2 negative zeros or no negative zeros. So help me fill it in. We look vertically. If we started with 0 positive and 2 negative, how many imaginary would we need? 2. For the last one, 4. Because we have no positive and no negative, which means every single graph or every single zero would be imaginary. So for this question, if I ask you to start, where would you guys start for checking? Negative solution. So I would suggest that you check for your negative solutions first. So right now, do the same thing for question number 2. Like me and Juan just had that conversation, you don't need to fill in the missing terms. Leave it as is and see as you're going from one term to the next, what do the signs look like? So you're looking at question number 2. All right, so let's look at question number 2. So I just want to know what are the possible positive answers and the possible negative. So we'll start with positive. How many possible positive answers will you have? 2 or 0. And then for negative? Just 1. Remember, if you subtract it, it won't work. You can't have negatives. So over here, I'm going to make my little chart. And I'll have positive, negative, and imaginary. So if I was to fill this in, we can either have 2 answers or no answer for positive. For imaginary, really we can only just have 1. That's the only possibility we can have. Since the degree on this is 3, that means you have a maximum of 3 solutions. So for this question here, if I was looking at this vertical, we can either have 2 positive or 1 negative, which means we'll have no imaginary. Or 2 what? Oh, you're going to the next one. So for this one here, if we have no positive and 1 negative, we would have to have 2 imaginary. You have to have it because every single time the max you can have is a maximum of 3. You don't have to write this down, but I just wanted to mention, let's say for this question here, it was x to the 4th power. I'm going to do it right on top. Let's say you don't have to write this down again. Let's say we had this little chart, and I'm completely making this up. Let's say we had 2, 0, 2, 0, 0, 0. For a problem like this, if you had a possibility for 2 positive and 2 negative, does it matter which one you start out with? No, because literally it's tied. That's why I'm saying Descartes' rule helps some of the time, like we saw with the other ones, because it'll help you figure out which one to check first. But if this was your table, it really doesn't matter which one you start with. It's going to either be positive or negative. It just depends. So, and I think I forgot to put this one to be a 4. That was my fault. Yeah, no, you're good. I was getting too excited and put zeros. But that bottom one should be a 4, which means there would be no imaginary. And especially since you can't check for imaginary, that's why it's not going to be worth it. Okay, before we flip over to the next page, I completely forgot about this bottom part here. If you had this table, what should you probably check first? I would check the positives. So we would check the positive answers first. All right, pretty good. All right, let's actually apply it. So we're going to take Descartes' rule and we're actually going to apply it to the next question. So that way you'll see if I gave you a problem that looks like this, how you would be able to graph using Descartes' rule. How is this useful? As I mentioned at the beginning, when we were solving questions last time and we had multiple answers, so like we had between, I don't know, 4 and for one of the questions, like 18 different possible zeros that we can use by the rational zero theorem. We're going to try to use Descartes' rule to kind of limit that a bit. So for this problem, here's my equation. I might not show you this equation too much because I'm going to be rewriting it at the bottom, but this is the equation I'm using, so check your paper, make sure you're on the right page. And we're going to use the following steps, which are A, B, C, all the way through G. Okay, so the first part is to use Descartes' rule to figure out the possible positive and negative real zeros. So down here, I'm going to recopy G of x. Yes, I'm recopying it. This is x to the 4th power minus 18x squared minus 32x minus 15. I need to check to see how many possible positive zeros I will have. So as I go from x to the 4th to negative 18, that's going to be yes, that's a sign change. From negative 18 to 32, that is not a sign change. And from 32 to 15, that is not a sign change. So it looks like for our possible positive zeros, there's only one. Only one possible zero. Let's do the same thing for possible negative zeros. So we're going to have negative x. I have to simplify. Anytime you raise a negative to a power of 4, so any even number is going to be x to the 4th power positive. We're going to have negative 18. If you do negative x squared, that turns into just an x squared. This one, you're really not using any exponents because the exponent's 1, so we're just going to multiply. Negative times negative will be a positive 32x. And then I'll put the 15 at the end. So what I need to check for, again, are sign changes. So Shreya, as I go from x to the 4th to negative 18x squared, is that a sign change? From negative 18 to 32? And from 32 to 15? Ooh, this is fun. So it looks like I have 1, 2, 3 possible negative zeros. So I'm going to put a 3 here. Is that the only possible number of negative zeros I can have? Or 1, because I could literally take 3, subtract it from 2, because you have to do it in even numbers. You'll either have 3 negatives or 1 negative. So let's make my chart. I think you guys have an idea, but let's make the chart. I'm going to put positive, negative, and imaginary. We already said for positive answers, there's really only 1. And if I try to subtract 2 from 1, it's not going to give me a whole or a positive number. So I just definitely want to keep that as a 1. For negative, we said we could have 3 or 1. And remember, at the very top of the page, what was the degree for this polynomial? 4. So I need to have 4 possible solutions. So far in this first column, I do have 4 possible solutions. So we're going to put 0 imaginary if that was the case. For the last one, though, how many imaginary would you need? 2. So if you look at this chart that I have, remember, imaginary is off limits. That just helps you with figuring out what other type of solution you might have. What should we probably check first? What sign? Negative. So let's check negative first. That reminder will help you figure out when we do the rational zero theorem in part B, what numbers we should start out with. So that should eliminate about half of our answer choices. All right, so for rational zero theorem, if I was to write this out, Layla, looking at this equation up here, what do I need from it?
So your p-value is and then the p-value is
Where'd you get the 1 from?
it's invisible in front of the x.
Yeah, so your leading coefficient for this entire polynomial is a positive 1. So down here for my p over q, let me zoom in a bit. I'm going to make this negative 15 over 1. As we had the discussion before when we were looking at these notes, you don't have to simplify that negative 15 over 1 to make it any kind of other sign. You can just leave it like that, and we're going to put a plus or minus to compensate for that negative. Allie, what are the multiples for 15? 3 and 5. Anything else? 1 and 15. And then, not a trick question, what's the multiples for 1, Allie? 1. So if I ask you for the possible rational zeros, Allie, what would you tell me? And remember, to get those, all she did was divide the fraction that we have here. So luckily, since we only have 1 in the denominator, it was really quick. Okay, so technically with these answers, I have 8 possibilities. But I can narrow it down to 4. What answer should I only focus on? Negatives. It'll probably have a positive answer, potentially, but I'm just going to focus on the negatives because that'll help me when I'm using synthetic division. So that's that piece from last class that hopefully will help you guys solve these a little quicker. So down here, let's start with, I'm not going to start with negative 15, guys. Keep it simple. Let's start with negative 1. So with negative 1, I'm going to rewrite it, and I'm going to rewrite the coefficients for my polynomial. Juan brought up a good point. Is there any terms missing from this polynomial? What's missing? X cubed. So we're going to put 1, then 0, then negative 18, negative 32, and negative 15. From here, we're really only going to hopefully test 4 different answers, hopefully. So I'm going to bring this down. We're going to multiply, add, multiply, add, multiply, add. Wait. Did I do that right? Ha! I said 1 times 1 was 2. It's the same mistake y'all make. 1 times 1 is 1. I was like, that's not right. I am. Negative 17 times negative 1 is 17. And then 32 minus 17 is negative 15. Negative times negative is positive, which means I have a remainder of 0. Whew, if I would have kept that 2, we would have had a real problem. So what does that mean for 1? Negative 1. I'm making that note so you don't forget it. Okay, we tried negative 1. Do we need to try positive? We can if you want to, but we don't have to. We have a higher possibility of showing an answer is right if we try the negatives first. So let's try negative 3 next. So keeping what I have, we're going to put negative 3, and you guys do it. See if we have a remainder. Once we get to a trinomial, we don't need to keep using synthetic division. So after this, hopefully, we can just factor like normal. I got negative 3 was a 0. Is that right? Okay, good. I do want to make sure you remember, keep in mind, guys, if you want to factor this four-term polynomial, you can. But the issue is you're risking not being able to completely simplify it. I would suggest if you have 4 terms, even if you could factor this by grouping, I would still do synthetic division one more time to get a trinomial, because at least if you get this and you can't factor, you can always use quadratic formula or completing the square. Okay, so let me write out my other note. X equals negative 3 is another 0. So let's take what I have here. This is my constant, x to the first and x squared. Let's factor. So I'm going to write this as x squared minus 4x minus 5, and we're going to solve. So I'm going to make my little x chart over here to the side to factor. I need to find two numbers that multiply to negative 5 but add up to negative 4. Thank you. Since this leading coefficient is a positive 1, I don't need to factor by grouping from this point. All I need to do is take x minus 5 and x plus 1, if I can write that correctly, and set it equal to 0. By the zero product property, we're going to take x minus 5, make that equal to 0, and x plus 1, make that equal to 0. What are the other two x-intercepts? Positive 5 and negative 1. So to write this out, I have pretty much all of my zeros. I have them listed out. I'm going to now write my equation in its factored form, and then we're going to finish it up. So if I was to write these in factored form, I have an x equals 5, I have an x equals negative 3, and I have two x equals negative 1s. Jory, how would I write that as an equation? We can put g of x. Let me actually write g of x. You could put g of x or y. So g of x will equal. Okay. Minus 1? Minus 5. Okay. Minus 5. Okay. Especially since your leading coefficient for this one is a positive 1. When you FOIL all of this out, it should be a positive 1, but we could put a positive 1 in front too, just to make sure. Because if you look back at the top, in front of the x to the 4th power, it is a positive 1. All right, it's asking for the solution, so I'm just going to write these out. My solutions are x equals 5 with the multiplicity of 1. X equals negative 3, again with the multiplicity of 1. And x equals negative 1, this one with the multiplicity of 2. So if I was to write my end behavior, I have to zoom in down here. For my end behavior, I have a leading coefficient that's positive 1 and a degree that is positive 4. Aaron, if I have a leading coefficient that's positive 1 and a degree that's 4, what's going to happen to the ends? You have a positive leading coefficient and an even degree. Both go up. Good job. And then one last question, Aaron. What's the y-intercept for this equation? Negative 15. With all of this stuff, guys, you can graph it without me. You don't need me to help you graph. We've labeled the x-intercepts, which are the solutions. We've labeled the end behavior, the y-intercept. You can graph this. So right now, take all of the stuff I have on my screen and graph it. So I have all of my items marked. I'm going to start creating it. It's going to start in an upward direction. It's going to go down towards negative 3. We said this has a multiplicity of 2, so it needs to cross. At negative 1, this should bounce off of the x-axis. It needs to go down through negative 15. And I'm going to kind of make it go a little lower so I can come up to 5 and have it cross through. So this might not be the most beautiful graph, but it shows what I'm looking for. Both ends are going up. It has the following x-intercepts, and it crosses at negative 15.
It's another wonky W.
Yep, it is a wonky W. So give me some nods or shakes. Does this make sense? Descartes' rule isn't, I will say it again, Descartes' rule isn't always going to be helpful, because remember, on the front side of this page, when we had both of these 2's, it really wasn't helpful for helping us decide which one we should start with. But if you're lucky like the ones that we've seen here, If you notice that you have one priority over another, so if it's showing more positive answers than negatives, I would start with the positives or vice versa. So just make sure when you guys have questions like this, use Descartes' rule as a guide of if I'm doing synthetic division with rational zero theorem, what number should I start out with? Are there any last questions? Awesome.